For a century, industrial design perfected the permanent joint. Adhesives, welds, and overmoldings proved that permanent assemblies could be cheaper, lighter, and stiffer than anything meant to be taken apart. But look across the industry today and you'll spot a quiet reversal. Suddenly, designers are focused on how a thing comes apart, or whether it needed to be joined in the first place. This shift moves the decision-making from the waste facility to the concept desk. It is a choice about structure, independent of the recycling story. This requirement to eventually unjoin components forces decisions that must be solved during the concept phase, long before a product hits the factory floor. Mastering planned deconstruction changes how a designer approaches a blank canvas. If a product must eventually be undone, the assembly strategy dictates the first sketch. To see how rigid these downstream spaces are, look at the environment where conceptual design meets physical limitation, a legacy factory floor. Take an existing combustion engine body shop, like Hyundai's Izmit plant. Feeding a new electric vehicle into a line built for gas cars immediately exposes a spatial conflict. The factory is rarely neutral. The physical tooling and automated tracks built for older platforms cap how far the proportions of a new EV can stretch. You find similar physical restrictions in transport logistics, specifically when engineering a modular structure like a house-a-home. This modular house unfolds from a wireframe shipping container. The packed envelope governs the entire design. Fitting inside a carton at architectural scale forces a specific joint strategy. The connections must survive being built, dismantled, and packed away, over and over. These logistical spaces act as a cage around conceptual freedom. Designers must plan for disassembly and transport before the first wall is placed. That same logic applies when we scale down from logistical cages to the invisible physical forces acting on individual components. Canova engineers landing legs using filament winding. Material density increases exactly where simulated stress arrows point to concentrated loads. Because structural analysis dictates where fibers cross, it becomes the external pattern. It is a direct readout of physical forces, untouched by a stylist. We can see this tension between structure and style in the automotive lamp, currently the largest brand identity surface on a modern car. Today, a headlamp is a permanent, bonded stack of optical polymer, diffusers, housing, and heat sinks. Once glued together, these materials cannot be separated. Projects like Covestro's Collect are working to make these components fully separable. Designing for disassembly removes the requirement that every layer be chemically or thermally compatible for bonding. Removing the glue allows designers to mix a wider variety of polymers and optical layers that would normally fail the bonding process, moving the constraints on what a brand's signature light can be. This means that factory lines, shipping boxes, and component physics all collide at the start of a product, the concept phase. Look at this Depix design study. It is a motorcycle frame engineered from a single, continuous, filament-wound structure. There are no metal tubes or bolted joints here. Without any welds or brackets to rely on, the structural density steepens into dense crossings at the steering head. The shape is generated by physics, not styled by human hands. Standard generative AI models struggle with this logic because they often prioritize visual novelty over physical truth. Professional work requires strict adherence to how forces actually move through a material. To successfully design without permanent joints, a designer must anticipate the method of a product's physical undoing from the moment of conception. Because, in the end, design decisions are cheap as a sketch, brutal once tooled. See every angle before you build. This conceptual freedom is powered by Depix.